This contraption is a replication of the idea of what's called a Noria, a very ancient device used to transport water from one level to another. And you can see in this case, every time I turn the wheel, these cups gather a little bit of water and they pour them or dump them into a tray, and the tray delivers water to an aqueduct or some source. The difference in height from where the cup comes from to where the cup is delivered is a small distance that can be measured, and the amount of water that's delivered can also be measured by measuring how much water goes from the cup into the vessel here or off into the aqueduct. The engineering of this is proof of concept. In other words, we're trying to replicate an ancient technology using simple materials. And so what we have here are two pie plates that are stapled together or glued. In this case I've glued and stapled. Every cup is glued into the pie plates, and then in between the pie plates and the cups I've stapled them so that there's space in between each cup. A dowel goes through the center and is reinforced with a piece of foam and glued in the middle. The bearings are made by just a twist of wire with duct tape on each side, and you'll notice it's on an angle so that the water can dump at an angle and ultimately go into this aqueduct system. The most variable is in how the aqueduct is set up, and so that's free-flowing, and it's something students would have a good time trying to figure out what the best combination was and how close they could get it and how much efficiency. So the first experiment that I would do would be figuring out efficiency. As you turn this, each cup pulls up a certain amount of water, and we can actually measure how much that water is by taking the bearing out, looking at the cup on the side and measuring how much water is in the cup, or dumping it into a graduate cylinder. So for every revolution we know, or for every cup dump, we know how much water is supposed to be in there. So if we put our aqueduct here and we start to dump water the best we possibly can, you can count how many revolutions and how much water is supposed to dump into the aqueduct, and then ultimately how much water comes out. In the experiments that I did preliminarily on this system and getting it as close as possible, I got about a 72% rate, so that means that we're losing about 28% of the water as it goes from place to place. The other thing that's fun to do is to take this system and determine how much force and work is being done by moving the handle. Every time I move the handle, there's a certain amount of force through a certain amount of distance. So I can measure this by taking a spring scale. And taking a spring scale, I can measure at a tangent to the circle the force, in which case it's a little over 0.2 newtons. With some calculation and with some control of your CGS units, you can figure out how much work is being done per revolution then. Contrast that with how much work is coming out. You can actually take and figure out what distance we have the water is coming from here to the surface of the water. So that's our distance. We know how much mass is in the water because we know how much water per dump that we get. And we know our relative efficiency rate, which is only about 72%. So what we can do is we can use our CGS units, figure out what our mass gravity height is, figure out what the potential energy and total work done by one revolution. And again, efficiency can be calculated, and in this system we end up with about a 40% efficiency rate in terms of work done here and work received out. So lots of fun things you can do with an example of an ancient Noria.